In this video, we're going to try to figure out how the driving point impedance of transmission line changes when we add different lengths of transmission line to a load. We've already looked at how the reflection coefficient changes when we add transmission lines to a load, and this video is tightly related to that idea. Here we're looking at how impedance changes with lengths of transmission line, which is what causes our generalized gamma to change as we add transmission line. So the behavior in this video is the root cause of the behavior in our generalized gamma video. The voltage standing wave pattern is what causes changes in impedance with transmission line length. I've drawn two transmission lines with standing wave patterns on them to show that. The driving point impedance is set by the ratio of V of minus st over I of minus st on this line, which is equivalent to saying that the driving point impedance is the impedance such that the voltage divider ZDP over Zs plus ZDP results in the voltage at V of minus st. This second definition is handy when we're thinking about ZDP for a sinusoidal wave, because we know that the amplitude of the waves is going to be set by the voltage standing wave pattern. And so we pick a ZDP that divides us down to the standing wave pattern. Because the standing wave pattern is periodic, ZDP is going to vary periodically as a function of length in the transmission line. You can see a suggestion of that on this slide. On the top schematic, the driver sees an antinode in the voltage standing wave pattern, which means ZDP needs to be big. The bottom line contains more of the standing wave pattern such that the driver sees a node, which means ZDP needs to be small. If the line length were somewhere between these two, you would tap into a different spot in the standing wave pattern, which would require a different ZDP. Or if the lines were exactly one wavelength longer, you'd be tapping into the same spot in the pattern, implying the same ZDP. That's a little complicated, but there's a silver lining. Even though the standing wave pattern makes ZDP change with length of the transmission line, the fact the pattern is a standing wave means ZDP doesn't change with time. Also, though these pictures are great, we need a mathematical model to let us do more interesting calculations. I've brought over an image of the transmission line to help us start making that mathematical model. I've also added some arrows indicating the current flow at the source and the load. We know that ZDP of S is given by V of minus st over I of minus st, but that's a tough place to start this calculation because we don't know the voltage and current at minus S. Instead, we're going to use the same approach we used on the generalized reflection coefficient. We'll calculate the voltage and current at the load, and then propagate those back to the driver to find the ratio there. Our first set of equations is all about rearranging the voltage and current at the load. We know ZDP of S equals 0 is given by V of 0t over I of 0t, and we rewrite those as left and right traveling waves in this second expression. We can factor V plus out of the top equation and I plus out of the bottom to get the equation in some rather handy forms here. The V plus over I plus ratio in front becomes Z naught, while the V minus over V plus and I minus over I plus ratios are each given by the reflection coefficient, which I've chosen to write as the generalized reflection coefficient at length 0. That form suggests that finding ZDP at point S is as simple as substituting our expressions for generalized gamma into the ZDP of S equals 0 equation. We do that in this second set of equations and wind up with a tidy looking expression for ZDP. We can simplify this expression further, and we're going to do so on this page. First, we're going to skip a lot of algebra in order to rearrange this expression in terms of ZDP over Z0, which we call our normalized driving point impedance. Second, we're going to combine the complex exponentials into hyperbolic tangents, which gives us a general expression for the normalized ZDP. One of the cool things about this derivation is that it works for lossy lines, and you'll notice that this expression depends on gamma rather than just the wave number. However, the expression for lossless lines is somewhat easier to deal with. You can see from the combination of sines and cosines in this final expression that we'll be tracing out some kind of circle in the z-plane as s is increased. This formula has some wild implications. The first and most commonly used is that matched loads always have a driving point impedance of Z0 regardless of what S is. In a matched load, these two ZL over Z0 terms would turn into 1, and the right side would just cancel to 1. This is really useful when interconnecting RF systems. It means that the cabling or routing won't affect your performance. And so RF systems are often designed to be matched loads in order to take advantage of this. Second, if you have a quarter of a wavelength on your line, then the tangent of Ks is infinity, and we find that ZDP is equal to Z0 squared over ZL. So by adding some transmission line, we have inverted our impedance. That's weird for resistors. It's really weird for open circuits, which become shorts, and it's really, really weird for capacitors, which start to look like inductors. All of those are fun party tricks. Finally, tangent is periodic in pi, so every additional half wavelength we add to our transmission line gives us the same ZDP. So in summary, the driving point impedance of a line varies periodically as a function of the length of the line, according to a pretty tricky equation. The driving point impedance of terminated lines doesn't change with length, which is really useful for connecting RF systems to each other. And finally, this driving point impedance transform is capable of making some strange impedances.